Hi, everyone. Welcome to the online causal inference seminar. Today, we have the pleasure of having a talk by Lauren Dang from UC Berkeley on integration of observational and randomized controlled trial data, approaches, challenges, a novel estimator, and application to the LEADER cardiovascular outcomes trial. So we look forward to that. After Lauren's talk, we will have a discussion by Robin Evans from University of Oxford. Hopefully you will find all of these talks interesting, and if you have questions, please submit them through the Q&A. I will now pass on to Chingyuan, who will be handling questions today.
Okay, I guess there's not much else to say besides that please use the Q&A tab, which is located at the bottom of your Zoom, to submit your questions. So we'll be able to keep track of the questions, and I'll stop Lauren from time to time to take questions. Please don't use the chat box unless you want to say something directly to us. Without further ado, Lauren, please take it away.
Thank you so much. Okay, can everyone see my screen?
Yes.
Okay,
Looks
excellent.
great.
So thank you all again for having me here today. I am going to talk about integration of observational and RCT data. I'd like to thank all of my collaborators, Jens, Edwin, Kim, Trina, Kaisa, John, Maya, and Mark. And by way of disclosure, this work was funded by Novo Nordisk. So as we all know, the randomized controlled trial has long been considered the gold standard for evidence generation. But sometimes running an adequately powered RCT may simply not be possible, as might occur with rare diseases, or unnecessary randomization to control may be considered unethical, or at least highly undesirable to patients. Cases where the latter may occur include pediatric approvals of medications that have previously been shown to be safe and efficacious in adults, severe diseases with unmet need where randomization to control is effectively randomization to very little treatment, or secondary indications for previously approved medications, especially when they have been shown to be effective for that indication when administered in a different route. And so in these kinds of cases, the hybrid randomized external data design is becoming increasingly popular. And the idea is to augment a small randomized controlled trial with external data, either from a previous trial or from some real-world data source, in order to minimize the number of participants who are required in the trial control arm or in the trial in general. Yet, of course, there is this risk of introducing bias anytime we introduce observational data into our analysis. And so the question becomes, how can we incorporate external data while still identifying a causal treatment effect? So to discuss this question, I'm going to set up this problem of augmenting an RCT with external data from a causal inference perspective. And I'm going to focus on the case where we only have additional controls, as might occur if the medication has yet to be approved, but these methods also work if you have active treatment in the real-world data source as well. I'll explain challenges in selecting an optimal combination of RCT with or without external data, and introduce the cross-validated targeted maximum likelihood estimator that we have been working on for this context of data adaptive experiment selection. I'll then demonstrate an application of this estimator to a reanalysis of the effect of liraglutide, a diabetes medication, on glycemic control from the LEADER trial. And as we said, please feel free to jump in with any questions. So first, some notation to make sure we're all on the same page. We have a set of baseline covariates W, and we have multiple potential data sets S, where S equals 0 is an RCT, and then we have one of K potential real-world data sets. We then can define multiple experiments that we could analyze to estimate the effect of interest, where those experiments include the RCT with or without real-world data. We have a binary treatment A, where A equals 1 is the active treatment and A equals 0 is standard of care, and an outcome Y. And each of these variables may have its own unmeasured exogenous error, U. So then our observed data O has a true distribution P0. Okay. Now, just to remind ourselves what we are interested in, we're interested in understanding counterfactual outcomes, where Y1 is the outcome an individual would have had if prescribed active treatment, and Y0 is the outcome the individual would have had if prescribed standard of care. So for this presentation, what we are interested in for our causal parameter is the average treatment effect. Okay, so we want to identify the average treatment effect from our observational data. And while there are multiple necessary identification assumptions, the primary challenge in this context is this assumption of mean exchangeability over S. So what that means is we need the conditional mean counterfactual outcome under treatment level A, given W and S equals 0 being in the RCT, to be the same as the conditional mean outcome of the counterfactual outcome given W and being in this combined experiment for every level of our treatment. And so in this specific case where we only have extra controls in the observational data, what that means is we need there to be no direct effect of being in the trial versus the real world on our outcomes, and no unmeasured common causes of being in the trial versus the real world and our outcomes, because any of these factors could introduce bias into the analysis. It also suggests the importance of a hybrid design that is designed prospectively so these data sources are compatible. Because we have to think about things like how healthcare is paid for in the RCT versus the real world. Are patients more closely monitored, or are their outcomes measured differently? And it also suggests that the best way to design these two studies might be to design the RCT to have as many pragmatic elements as possible. That is, to mimic real-world healthcare in as many ways as we can make it mimic the real world. And then, of course, we have to think about how patients are selected into our trial, and not just obvious things like the trial inclusion and exclusion criteria, but also less tangible things like, do patients have better access to healthcare for those who are able to access the trial versus those in the real world? So even if we've really considered these things and designed these studies to go together well, there still is this question of whether or not we actually succeeded. And that is where data fusion estimators come in. So these types of estimators can be useful when our identification assumptions are plausible but uncertain. And they provide greater protection against bias than a purely observational analysis, assuming that those assumptions are in fact true. The way these estimators work is that they provide evidence of bias to decide whether to include real-world data or how to weight the real-world data in the combined analysis. And while they'll estimate bias in different ways, it all boils down to some comparison of the mean outcome or conditional mean outcome between RCT and real-world data controls. So this is an exciting field. There are more and more of these estimators all the time, and I am fortunate that Robin is going to go into detail about some of these estimators at the end of my talk, so I won't spend too much time on it. But I will say there are several large classes. One is the Bayesian dynamic borrowing class of estimators, where a prior distribution of the mean outcome under control is based on the external data. Then there are all of the test then pool approaches, or equivalence-based placebo test approaches. And in the simplest form, we include the real-world data if we don't reject the null hypothesis that the RCT and real-world data control means are the same. And if we do reject the null hypothesis, then we analyze the RCT alone. And many people have criticized this approach because we may not reject the null hypothesis simply due to low power with our small RCT. And that's where the equivalence-based placebo tests come in to address that problem. But nonetheless, it's kind of an interesting comparator as a high-risk, high-reward approach, and we'll see that in the simulations. Then we have a series of estimators that aim to optimize the bias variance trade-off of including real-world data in the analysis. And these estimators have noted this inherent trade-off between the power increase that can be achieved when unbiased real-world data is available and our ability to control type 1 error across all potential magnitudes of real-world data bias. And we'll again talk more about this coming up. So this isn't a foolproof solution, but it's still a great place to start, and that's where we started as well. So I'm going to talk about our experiment selector with this goal of optimizing the bias variance trade-off. So to think about approaching this problem, we consider that the mean exchangeability assumption may be true for some of our experiments, but not others. And for any experiment, we can define a causal estimand as the average treatment effect for that experiment, where we're interested in the difference in counterfactual outcomes under treatment and control, but averaged over the covariate distribution represented by that experiment. That's our psi-F causal parameter at the top. We then can define, using the G formula, a statistical estimand for this average treatment effect using our observational data. That is this psi parameter below. And if our causal identification assumptions are true, then psi is equal to psi-F, and we can identify this effect from the observed data. But we're not certain whether or not that's true. Nonetheless, we do have some information from the observational data about another causal parameter. So because we know that the mean exchangeability assumption is true in the RCT, if we define a different causal parameter as the mean difference in counterfactual outcomes, assigning treatment A is 1 versus A is 0, but also assigning patients to be in the randomized controlled trial, S equals 0, then if we take that difference, again averaged over this same covariate distribution represented in our experiment, we get this psi tilde F causal parameter. And because mean exchangeability is true in the RCT, that causal parameter is equal to the statistical estimand psi tilde that is equal to the difference in conditional mean outcome given A is 1, S is 0, and W, and the conditional mean outcome given A is 0, S is 0, and W, again averaged over that same covariate distribution. So we might be tempted to say, well, why don't we just estimate psi tilde? And we could, but the information bound for that parameter is determined by the sample size of the RCT. So we can't actually gain efficiency compared to estimating the sample average treatment effect from the RCT alone. We can, however, define a causal gap, that's this psi pound, as the difference between our psi average treatment effect estimate in the combined experiment and our psi tilde estimate that we know is equal to a causal parameter. And again, we might be tempted to just correct our average treatment effect estimate by subtracting our psi pound bias estimate, but then again, we're estimating psi tilde and we can't gain an efficiency. Now, Robin will talk about an interesting method that makes some parametric modeling assumptions about a bias correction function. And if you're willing to make those kind of assumptions, then you can gain efficiency. And it's a very interesting approach. But we are not going to make those assumptions, so we are just going to proceed forward, knowing that we can estimate this psi pound bias parameter and consider how we can use that if our goal is to develop an experiment selector to optimize the bias variance trade-off. So we want this selector, our SN star, to be the minimizer over all experiments of our estimate of the variance plus our estimate of the bias squared. And if we knew the bias, then we could do this really well. We could always include data that would add efficiency while always excluding data that would worsen our coverage for the causal effect. But we don't know the bias, we're estimating it. And so just to review why that's a problem, this is a very simple example, but the concept applies for any of these data fusion estimators. And that is in the top row, if we have the distribution of sample estimates for the mean outcome under control for an unbiased versus a biased real-world data set. And in the bottom row, we have the distribution of sample estimates for the mean outcome under control from an RCT. Most commonly, if we take one sample of unbiased real-world data and one RCT sample, then our estimate of the bias will be small and we will accept that real-world data. And most commonly, if we take one sample of biased real-world data and one RCT sample, our estimate of the bias will be large and we'll reject that real-world data. However, not uncommonly, we will take one sample of unbiased real-world data and one RCT sample, and our estimate of the bias will be large, so we'll reject that good real-world data. Or we take one sample of biased real-world data and one RCT sample, our estimate of the bias is small, and we accept that real-world data. So any of these estimators, no matter how they estimate bias, construct confidence intervals, etc., will struggle with this challenge. And this leads to the inherent trade-off that I mentioned earlier between the efficiency gains that are possible with unbiased real-world data and our ability to control type 1 error regardless of the magnitude of bias. So different estimators take a different approach to this problem. Many of them, in fact, will just have one method of estimating the bias and integrating that real-world data into the analysis and constructing confidence intervals. And I think you'll see in Robin's slides that different estimators will strike a different balance of these two factors. Then there are some approaches that allow the user to specify a tuning parameter indicating confidence in the external data. So a good example is the meta-analytic predictive priors approach of Schmidli et al. And this approach is really interesting. They have a very user-friendly R package, so I very much like this approach. But it's a little challenging because it's kind of subjective to think about your confidence in the data. Are you 50% confident? Are you 70% confident? I find it a little hard to tell. And it also makes it more or less likely that you will include any external data in the analysis, depending on how you specify this parameter. So these challenges led us to ask whether there might be another objective measure of bias that we could incorporate into our selector. And for that, we turn to the estimated average treatment effect on a negative control outcome. So an NCO is not affected by treatment, but is affected by other unmeasured factors that are causing bias. And they're mostly used for observational analyses and rely on the following assumptions. If those unmeasured factors causing bias are the same for the treatment outcome and treatment negative control outcome relationships, then we have U comparability. And if the magnitude of the effect of that bias on the AY and the ANCO relationships are the same on the additive scale, then we have additive equiconfounding. And multiple authors have noticed that bias adjustment can be accomplished through a difference in differences approach. But if these assumptions aren't true, then our estimated average treatment effect on the negative control outcome, called phi hat here, is some percentage of the bias, but we're not sure exactly what. I will say there are some even more complex methods for dealing with this problem, but in the interest of time, I'll keep going with that. So again, we can still make use of this information, this phi hat estimate, in our selector, either by using it as our sole bias estimate, but again, if these assumptions are wrong, that might not exactly be accurate, or we could add it to our psi-pound bias estimate. And so that means that our bias estimate psi-pound plus phi-pound is not exactly the true bias, but this is intellectually similar to the concept of adding a penalty term with the bias term in this selector so that the selector prioritizes minimizing bias over minimizing variance. It's just that the penalty is determined by this average treatment effect on the negative control outcome instead of a parameter that we specify. And the reason this might be helpful is that including the average treatment effect on the NCO can help us to include unbiased real-world data and exclude biased real-world data. So to see why that is, if we look at our sample distributions of our estimates of the ATE on the negative control outcome from our RCT in that thick gray line, and then our RCT plus unbiased real-world data with our thin black line that is also centered around 0, because of the increased sample size by adding the real-world data, this estimate is more precise. And so having this estimated average treatment effect on the NCO in the selector helps us to include the unbiased real-world data. Yet the average treatment effect on the NCO is not truly 0. This statistical estimand is not truly 0 with our biased real-world data. And so again, having that in the selector can help us to exclude the biased data. We'll see how this plays out in a simulation when our NCO is not actually perfect. Okay, so now we know a couple of selectors we could use, but we need to use the data both to select the correct experiment and to analyze its results. And for that, we have developed a cross-validated targeted maximum likelihood estimator for this context of data adaptive experiment selection. So our goal here by choosing this estimator is to maximize our efficiency and minimize the statistical assumptions that are necessary for this estimator to be consistent. And in order to achieve those goals, we turn to a targeted maximum likelihood estimator. Now, this talk is not really about TMLE, so I don't have a lot of details, though I'm happy to answer any questions. But just by brief way of background, TMLE is a doubly robust plug-in estimator where we get initial estimates of the outcome regression and treatment mechanism using the superlearner machine learning prediction algorithm. So we don't need to rely on parametric modeling assumptions. And then we target initial estimates of the conditional mean outcome given treatment and covariates to solve the efficient influence curve for our target parameter, thereby optimizing the statistical bias variance trade-off for the target parameter. And cross-validated TMLE was previously developed for accurate inference for other data adaptive target parameters. The idea being to separate the parameter definition and the nuisance function estimation from the effect estimation using cross-validation. So these previous examples are extremely useful, but we have a little bit of a different challenge here, which is that we have to use the data both to select the optimal experiment and to analyze its results. And that provides additional challenges, particularly for inference, which we'll see coming up. But the main setup here is one of cross-validation. So we divide the data into V folds. And in every fold, we have an experiment selection set that is V minus 1 over V, usually 9/10 of the data, and an estimation set that is the remaining 1/10 of the data. So in each experiment selection set, for each experiment, we train superlearner estimators of the relevant outcome and treatment mechanism regressions. We also estimate the bias using TMLE based off of that psi-pound parameter we previously saw. And we also can estimate the average treatment effect on the negative control outcome. Then we estimate the variance of our ATE estimator for each experiment, and we select the experiment with the lowest estimated bias squared plus the variance. Then for each estimation set, we take data from the selected experiment, and we use TMLE to estimate the average treatment effect. So our final point estimate is the average of these fold-specific ATE estimates for the experiment selected in each fold. Now, getting the point estimate is actually not the most challenging part here, because we need to construct confidence intervals that take into account the fact that there may be non-negligible bias sometimes when real-world data is incorporated into our analysis. And for that, in order to understand this finite sample behavior of our estimator, we really need to understand how the estimator behaves asymptotically when bias depends on sample size. So if we look at this standardized version of our selector here, where we've multiplied it by n and added and subtracted the true value of the bias term, this psi-pound, then we need to consider how the estimator behaves depending on the behavior of this root n times the true bias term. So considering 3 different scenarios here, if root n times the true bias converges in probability to 0, mimicking a case where bias is much less than the standard error of the estimator and so negligible, then our experiment selector converges to a mixture of normal distributions that we can learn from the data. If, however, this root n times the true bias converges in probability to a constant, mimicking a case where bias is approximately the standard error of the estimator, and so that real-world data might be included, but it might have bias of a magnitude that could impact our causal coverage, then the experiment selector converges to a mixture of normal distributions that depend on this unknown bias. And finally, if our root n times the true bias converges in probability to infinity, mimicking a situation where bias is much larger than the standard error, then that external data is deterministically rejected, and our experiment selector converges to a normal distribution that is equivalent to running a CV-TMLE on the RCT data alone. So to handle these cases, we construct confidence intervals via Monte Carlo simulation from this estimated limit distribution. And I'm happy to go into more details about that process. But one thing I want to point out is that because we don't know the true bias, we plug in our estimate of the bias into this sampling procedure where this root n times the true bias term would be. And the result of that is that we are overestimating the bias if it is truly 0 just due to finite sample variability. And so our confidence intervals are actually conservative in this case where we have truly unbiased data. But that's the price that we pay for having reasonable confidence interval coverage when bias is non-negligible. And again, we're going to see how that plays out in the simulations. Okay. I think I actually will pause just for a moment here and see, does anyone have any questions at this point?
Yes, Lauren, we do have a question. I guess it's about the setup of the problem. So this is from an anonymous attendee. What if the causal estimates are unbiased in both the randomized control trial and the observational data, but actually differ?
Yes, that is a great question. So I'm just going to scroll back up to the slide where we looked at our causal parameters. Okay, so if the effects are causal effects, but they differ, then we have these psi-f parameters that are causal parameters, but that are different in the different experiments. And so the challenge here is if we are only adding extra controls to our analysis, then we don't have any way of knowing, besides our causal assumptions, whether psi-f, the causal parameter, is equal to psi, the statistical estimand. The only information we have from the data itself is whether this psi tilde, which is equal to this statistical estimand psi tilde, is equal to our estimate psi. And the reason that's important is if the true causal effect is different, if it is just a difference in the conditional mean outcome, given A is 1 and given A is 0, if the conditional mean outcomes, if the difference in conditional mean outcomes are the same, but once we average it over a different covariate distribution, that changes the effect overall, marginally, that is something that we can still estimate from the data. But if there is a different true causal effect, for example, if being in one of the studies versus the other modifies the effect of treatment on the outcome, then we can't actually estimate that from our available data. So we might end up rejecting the real world data in a context where the causal effects are just truly different, rather than because there is bias. And that's because the way that we are estimating the causal gap is dependent on this causal parameter psi tilde and not on the causal parameter for the average treatment effect psi. So I'm not sure if that totally answered your question, but I think the take home from all of that is it is possible that with this method of estimating the bias, we reject the real world data because the causal effects are different and not because there's bias, because the way that we're estimating the bias is based off of this alternate causal parameter and not the causal average treatment effect.
Yes,
Does that answer the question?
Well, we don't know who is the person who asked the question, but maybe let me switch to another question before you move on. I think this is related to what you're going to talk about. Could confidence intervals be constructed in some other way than the Monte Carlo simulation you're perhaps going to describe? Yeah,
so one thing that we considered originally was whether we could do it with the bootstrap, but there is a good paper by Yang et al. Where they have a similar context. It's actually slightly different and prove that the bootstrap is actually not consistent, and it has to do with the kind of procedure for sampling from this mixture distribution. So we decided not to go that route. We actually initially did that. I will say, because I initially did it, you actually get pretty close, but it's not theoretically the best way to approach the problem. And that's how we ended up with Monte Carlo simulation from the estimated limit distribution.
Okay, thank you. We don't have any further questions at this point.
Okay, great. So thank you for all of your questions. I'm going to go back down to where we were. Okay. So just to recap where we are right now, we know what criteria we want to use to select an experiment. We have an algorithm for selecting and analyzing that experiment, and we have a method of confidence interval construction. So how does this estimator actually perform? Well, I know that the best part of everyone's day is probably looking at the setup to simulations. So I'm just going to highlight what is important about this simulation setup. We have a small simulated RCT with a sample size of 150, 3 simulated real-world data sets with sample size 500. Our treatment in the RCT is randomized with a probability of 0.67, mimicking this case where we want to assign more patients to active treatment. And in the real-world data, everyone gets control. We then need to simulate bias of different magnitudes and a particularly tricky amount of bias where we might expect that that real-world data would be included, but it could impact our causal coverage, is bias that is about equal to the square root of the difference between the variance of the ATE estimator for our RCT and the variance of the ATE estimator for our combined experiment. So we'll call that B. Then we have an unbiased real-world data set, S equals 1, a real-world data set with this kind of tricky magnitude of bias, S equals 2, and a real-world data set with large magnitudes of bias. And then just to make things even more complicated, we have 2 bias terms, and the reason that that is important is that our outcome is affected by the treatment and both bias terms, whereas our negative control outcome is only affected by one of the bias terms. So that's important because we not only have varying magnitudes of bias, but our U comparability assumption that we need for this NCO is not actually true. So we're going to compare the experiment selector to a test then pool approach, an NCO-based difference in differences approach, and in the preprint also a Bayesian dynamic borrowing approach using this simulation. And these are the results of 1,000 iterations of this simulation. I'm going to focus on coverage and power just because the variance estimation is actually one of the trickiest parts of this. So if we compare to a CV-TMLE for the RCT alone, which has coverage of 95% and power to detect the true effect in this simulation of 64%. If we look at a test then pool method, you can see that with unbiased data, we can increase our power all the way up to 93%, but with bias of this tricky magnitude, coverage falls to 79%. So again, this process definitely has limitations, this test then pool method, but I'm showing it because it shows you how much you could potentially increase your power if you were willing to strike a different balance of this trade-off. If we then look at an NCO-based difference in differences approach, because our U comparability assumption is not true, when we have a large magnitude of bias in the external data, our coverage falls to 84%. Then we look at our experiment selector CV-TMLEs, and with our bias squared plus the variance selector, we are actually able to maintain coverage of 95% or higher through these 3 different data sets, and we get modest power gains up to 74% with that unbiased external data. Then, if we add our estimated average treatment effect on the negative control outcome to the bias term, if we have unbiased external data, our coverage is a bit conservative as we expected, but we get power gains up to 83%. If we have a large magnitude of bias, that S equals 3 data set, then we reject that observational data and we're equivalent to a CV-TMLE from the RCT alone. And if we have this tricky intermediate amount of bias and our NCO is not perfect, our coverage falls a little bit to 92%, but we're still relatively close to nominal. So these last 2 examples are interesting because the balance you want to strike on your ability to improve your power and your guarantee of type 1 error control, regardless of the magnitude of bias, might depend on a variety of context-specific factors, like, can you run an RCT? What is the standard of care? What are patient preferences about type 1 and type 2 error control? All things that are sort of beyond the scope of this simulation, but you can use a simulation like this to help decide which estimator to pick, either ours or one of the many others that are out there. Okay, so it's nice to know how this performs. Oh, sorry, I forgot to mention, I did not show the methods that don't adjust for covariates just because they are relatively low power in this simulation where the covariates are somewhat predictive of the outcome, but those are in the preprint as well. Okay, so that's how it performs in a simulation, but let's look at how this estimator performs in a real data analysis. And for that, we're going to look at the effect of liraglutide, our diabetes medication, on change in hemoglobin A1C, which is a marker of how well your diabetes is controlled. We're using data from the LEADER trial. This was about 9,300 participants and originally reported by Marceau et al. In 2016. And this trial looked at the effect of liraglutide versus placebo, both in addition to standard of care, on a primary outcome of major adverse cardiovascular events, or MACE. But because this trial was powered to look at this relatively rare long-term outcome, it was extremely well powered for a short-term continuous outcome difference, as we might expect with change in hemoglobin A1C. So the trial serves as a relatively precise ground truth estimate for the effect on A1C. And we are going to set up this proof of concept for our experiment selector by taking small subsets of the LEADER trial to mimic underpowered RCTs, and then test the ability of our experiment selector to distinguish unbiased from biased extra controls. And the reason that we are able to do that is that trial clinicians were encouraged to add medications to lower hemoglobin A1C less than or equal to 7% in both arms. And it turned out that there was a higher baseline A1C in Central and South America versus Europe. And because additional medications were added, that led to a larger improvement in A1C in the placebo arm of Central and South America compared to the placebo arm of Europe. So if we were to take a small subset of Central and South America as our small RCT called CS, and then we were to add additional controls from Central and South America, randomized from the same region, we would expect them to be unbiased. But if we add additional controls from Europe, now this will make it look like there was less of an improvement in the placebo arm, and therefore it will make it look like there was a larger effect of liraglutide than there actually was, causing those extra European controls to introduce bias. So the next thing that we need is a good negative control outcome. And for that, we're going to try to understand what underlying factors are causing bias in our analysis. So we know that our outcome is change in hemoglobin A1C, and we're primarily interested in differences that occur in the placebo arm by adding these extra controls. And these differences in change in hemoglobin A1C were prompted by changes in other diabetes medications, which in turn were affected by baseline A1C. But we're going to treat baseline A1C as unmeasured for this analysis, so we have some unmeasured factors causing bias. And then we need to think about what other factors might lead to differences in baseline A1C between these two regions. So we need a negative control variable that is affected by these underlying factors causing bias. So if we presume that there were some social determinants of health or health systems factors that were underlying differences in control of baseline A1C, then these same factors may have led to differences in control of baseline cholesterol for patients in our study. Now, we'll note that baseline cholesterol is not affected by liraglutide versus placebo because it was measured at baseline. And while it is common and in fact generally encouraged to have a negative control outcome that happens later at the same time as your actual outcome, in this case, because everyone was enrolled in the same RCT, we really suspect that the factors causing bias occurred before baseline. So that's why we're using baseline cholesterol in this scenario. But generally speaking, you probably want an outcome that was measured at the same time as your true outcome. Okay, So we have all the ingredients that we need for this analysis. These are the results of 200 iterations of this real data analysis where we selected data with different seeds from the overall leader trial. And on screen left, we have the average treatment effect point estimates for each estimator with these different data sets across these iterations. And on the right, we have the confidence interval width relative to the confidence interval width from our small RCT sample. So if we look at first the median, or rather the point estimate from the full leader Central South America data set, serving as our kind of ground truth estimate, it was 0.97. And with our small Central South America RCT samples, the median point estimate was again 0.97, but there's variability across these iterations. And because the full leader Central South America data set was much larger, the confidence intervals are about a third of the confidence interval width for our small RCT sample. Then if we look at CV-TMLEs with no check for bias, with our unbiased Central South America data set, we have a median point estimate of 0.97 and confidence intervals that are about 2/3 compared to our small RCT sample. With the biased European controls and no check for bias, the confidence interval widths are again about 2/3, but our point estimate is severely biased at 1.33 for the median point estimate. Then if we look at our experiment selector CV-TMLE with the unbiased extra controls, our median point estimate is 0.96 and our confidence interval width is about 0.83. And so that intermediate efficiency gain is the price that we pay for checking for bias. But when we have biased extra controls, our median point estimate is relatively similar at 0.98, and our confidence intervals are 1 relative to the width of the small RCT. So in summary, when we have unbiased controls, we have more integration of that external data and our variance is improved. And when we have biased external controls, we have less integration and our variance is similar to analyzing the RCT alone. So in summary, the statistical challenge here is excluding data with bias approximately the standard error while including unbiased data. And this is a challenge for all of these data fusion estimators. But our experiment selector is relatively robust by optimizing the bias variance trade-off, though that is not unique to our estimator, incorporating information from a negative control outcome, not requiring any user-specified tuning parameters or modeling assumptions, using cross-validation, having a somewhat conservative procedure for inference, and being equivalent to running a CV-TMLE on the RCT alone when we reject that real-world data, so we don't lose power in that case. Nonetheless, we can't guarantee 95% confidence interval coverage, and so our recommendation is to estimate coverage with varying magnitudes of bias using outcome-blind simulations that mimic the proposed analysis as closely as possible if you're going to use this or any other data fusion estimator for a future study. So in conclusion, when a large RCT is not possible or excessive randomization to control is undesirable, combining a small RCT with real-world data and a data fusion estimator can improve our power while providing better protection against bias than a purely observational analysis. So if the question is this effect estimate truly causal? We're trying to move closer to the amount of confidence that we would have from just running an RCT, but we never get all the way there. Nonetheless, by using our causal roadmap and our experiment selector, we are relatively robust to violations of identification assumptions, make challenges for estimating the causal effect transparent, and obtain power gains when possible. So our R package is now on CRAN. Please feel free to try to use it, give me feedback, help me make it better. And I will also say this is a growing field with many exciting developments, and Robin is going to talk about some other approaches which are also really exciting. So thank you everyone for listening. I would like to thank all of the members of my working group, and I'd be happy to take some more questions or comments.
Yes, thank you, Lauren, for the nice talk. Maybe we'll just do 1 or 2 quick questions because I know Robin has a sharp stop later. So this one is from Archer Gongzhang. Is the real data public available? I think this is referring to the charge trial data set.
That's a good question. Unfortunately, it is not Novo Nordisk has their paws around that data set, but I know that Robin has it too, so we might see it for his estimator in the future.
Okay, so maybe just one short question from me. So is this phenomenon you demonstrated that you can not always get a sort of desired coverage rate related to the sort of super efficiency of the Hodges estimator? It's just reminds me of that kind of phenomenon. And
Ooh,
do you
okay.
have
So
any
in some ways,
comment?
this is kind of similar to a super efficient estimator, but I would love it if you would elaborate about that estimator. Tell us more.
Well, this is sort of it's an estimator that you sort of, if your estimator falls in a narrow range around 0, then you just sort of estimate 0, and then elsewhere it just keeps it fixed. And what happens is that in that particular parameter, you got super efficiency, you can converge much faster, but then in a small neighborhood around it, you got a slower convergence rate. And this is why you sort of you sort of assume the estimators are regular in these semi-parametric theories. But it kind of reminds me of that. But yeah, maybe we can discuss that later. And we should perhaps let Robin give this discussion first. Yeah, Robin, are you ready?
Yeah. Okay, can everyone see that?
Yes, looks great.
Excellent. So thanks very much, Lauren. It's a really great presentation. And I think the idea of using a negative control outcome as a way of assessing bias is a really neat idea. So I'm sort of basically going to start by just talking about a few different approaches that people can use, or people try to use to integrate randomized control trials with real world or observational data, as I tend to call it. So the first is where you're just targeting reducing the mean square error. So in a sense, doing the same thing that Lauren was doing, but instead of, coming up with a very elaborate estimator to do it, they basically say, okay, suppose I've got an estimate of my from my randomized data, which is maybe this red dot here, another estimate from my observational data, which is this dot over here. And I'm going to assume that the randomized data has quite a wide variance, and the observational data has a much smaller variance. So what you want to do is take a point that's along this line segment such that you're minimizing the total mean square error. So that's the sum of the squared bias and the variance of your estimator. And that's an approach that's used by Oberst et al., which I think Lauren cited in her talk. The second approach that people use is to shrink towards the estimate of the randomized trial from the observational data. So this is basically using Stein's method. And Stein showed that if you have a vector of independent normal random variables, and there's at least 3 entries, and you want to know, and you've only got 1 sample, and you want to know what the mean of that vector is, then you have a lower mean square error by shrinking towards some arbitrary point that you can choose. And you can use exactly the same idea to get a lower mean square error from a combination of a randomized unbiased estimate and an observational potentially biased estimate. So you shrink your biased estimate towards the randomized control trial. And that's was picked up by Evan Rosenman in the causal context just a few years ago. So those 2 I'm not going to talk about, but 2 I am going to talk about are experimental grounding, which is something that Lauren mentioned, where basically you make the assumption that there's some parametric model which will explain the bias due to unobserved confounders on your observational data set. And then the 4th one I'm going to talk about is the power likelihood, which is the approach that I've been using with my student Shi. And this is the idea where we sort of basically say we want something like a Bayesian approach. We've got a likelihood for the observational data and for the experimental data. But if we just combine them naively, obviously the observational data, if it's much larger, will just overwhelm the experimental data. So what we need to do is to raise that likelihood to a power we pick some power eta which is less than or equal to 1. So experimental grounding. So this was introduced by Callas et al. In a paper about nearly 5 years ago now. And the idea here is that you've got some estimate from your observational data, which obviously has to be conditional on the treatment actually being equal to the treatment in the counterfactual that you're estimating. And you want to say, okay, I want to model the difference between the difference of these two guys and the difference of this, which is what you would get from the randomized data, by assuming there's some parametric function phi of z, which explains that difference. And then what you do is you fit a model to your observational data, try and use it to predict what the outcomes would be in the randomized data. So if this is my randomized data, for example, and then I had a model which predicted something like this, then what I do is I look at the residuals here. As you can see, there's a sort of systematic bias as I move through some covariate that I'm interested in. So what you then do is then subtract the difference between those two curves in some parametric way. So typically this is done using least squares estimation. And they demonstrate this methodology on a randomized control trial called the STAR dataset, which is a study of Tennessee schools and the effect of having different class sizes. So what's great about this method is it means you can extrapolate outside the range of the experimental data. Obviously, if the model is misspecified, though, this means things can go pretty badly wrong. Okay, and then the power likelihood. So this is where we're going to use sort of a bit more Bayesian inference approach. And obviously the potential disadvantage of that is that Bayesian in some sense needs the model to be correct. And that's something we're not really able to assume in this context. So an approach that Bayesians have come up with for dealing with this is to raise their likelihood to a power eta, where eta is chosen to be strictly less than 1. And then, of course, the question is, well, how do we choose what eta should be? So our approach is to maximize a predictive quantity. So this is called the expected log pointwise predictive density. And it basically means you take your posterior distribution for a particular eta, and then you say, okay, how well can I predict another outcome from my randomized trial? So you leave one out cross-validation, fit the model, and then try and predict the thing that you left out, and you try and minimize, sorry, you try and maximize the log density under your posterior for that outcome. So this is very nice, but computationally it's extremely intensive. So for every value of eta, you have to do a separate Markov-Train Monte Carlo in order to generate the parameters in order to estimate this thing. So it's fine if you're only doing it once, but if you're doing a lot of simulations, it's a bit of a pain. So quickly talk about some simulations. So I'm not going to go on about this, but basically this is the true propensity score in the observational data set. This is the true propensity score in the randomized data set. And you can see we have this unobserved variable u, which will include bias if gamma is non-equal to 0. We have a randomized simulated study of 250 individuals and an observational data set of 2,500 individuals. And this is an estimate of the mean square error on the conditional average treatment effect. So this requires a little bit of thought. So the blue and pink estimators are the shrinkage estimators. So one of them is Green and Strawderman's original paper on this, and then the other one is from Evan Rosenman. And you can see they're doing what they should do, right? So this is the mean square error you get from the RCT alone. And you can see that when the bias here is 0, they do very well. They improve the mean square error. And then as the bias increases, they tend towards just giving you back what you get from the randomized trial data. On the other hand, we've got some parametric methods that includes ours, which is down here. And there's a sort of parametric benchmark, which is what you would get if you analyzed the randomized trial data under the correct parametric model. So in a sense, maybe this should be laid on top of this. But you can see that our method does very well. It massively reduces the bias at the beginning, and then it converges to be the same as the parametric benchmark. Callus's method does very well compared to just analyzing the randomized trial data alone, but not as well as ours. And then we can also look at the average treatment effect. And now we see that these methods, which were guaranteed to reduce the mean square error of the conditional average treatment effect, do not, in fact, reduce the average treatment, the mean square error of the average treatment effect. And that's maybe not surprising because, you know, there's no way to get a better admissible estimate than just using the mean, which is what we would do typically in a randomized trial. So the Green and Strawderman and Rosenman estimates are not very good here. And you can see that Callus's method, so actually, Lauren, of course, if the populations are the same, then you would expect that Callus's method will just give you back the same mean square error for the average treatment effect, because it's powered for the conditional average treatment effect. And you use the actual average treatment effect as a way to calibrate the error term. So it's not surprising then that Callus's doesn't do any better than just analyzing the real world, the randomized data under any magnitude of bias. And then you can sort of zoom in and see, compared to Oberst's method, so we do very well at first, and then we do very well later on, and there's just this little section in the middle where the bias is moderate in that tricky case that Lauren was talking about, which is very hard to deal with. Okay, and then very quickly, just talk about the STAR data. So this is a study of Tennessee schools where they compared, in the 80s, they compared having a small class with a regular size class at random, and Callus et al. Have this method of getting a confounded data set where you pick a variable which predicts the outcome strongly and then condition on it. And we did something similar, although we used a slightly less strong confounding, because if we use the strong confounding that they introduced, then it basically, our method said just not to use the observational data at all. But we end up with pretty strong confounding. So the naive estimate, just comparing the groups who were treated and not treated, gives an estimate of 57, whereas the original data set gives 30, just over 38. And so we can see that our method here, so this is looking at different values of eta. This going from 0 to 1. So 0 here means you just use the randomized trial data, and 1 means you integrate the observational data as though it were just as good as the randomized trial data. And the coloring here, so dark blue is the variance, and the red is the squared bias, which we know because we set up the data. And you can see that the eta we pick, which is this one, is pretty close to the minimum mean square error. So it's showing that it's doing exactly what we want. Okay, so enough of my method. So a couple of questions for Lauren. So one question I had, I sort of suspect the answer is probably you could. Is there some way to use the TMLE to kind of not incorporate a whole study, but just use part of it and get this kind of bias variance trade-off in a slightly more direct way? And then secondly, and it sort of seems like maybe you can if you make this assumption you talked about of percent change being the same, that you could use the negative control outcome in the same way that Callus and co use it to sort of subtract the bias you get in the conditional average treatment effect. So I just wondered whether you had any comments on those. Thanks.
Yeah. Thank you, Robin. And I'm very excited to see more about your estimator coming up as well. To answer your first question, so you could use our method to incorporate a smaller amount of information. We have just looked at, in this simulation context where you're comparing RCT alone to RCT plus the full data set, but the estimator will, in theory, consider any number of potential real-world data sets. And that's not just different data sets, but also you could do something like different numbers of propensity score matched extra participants, say getting kind of looser and looser matches, if you wanted to think about it that way.
Mhm.
It's not a continuous optimization of the weighting of the real world data and the RCT data, as you see in some of these other methods like Oberst et al. One reason I kind of like what we did is that you can really define what the target parameter is from a causal perspective for each of these experiments by saying, say it's like one propensity score matched group of people from the real world, that kind of defines who this target population is based off of the covariate distributions that are present in these data sets. And so your causal effect estimate for the combined data has this kind of defined target population. And then you do end up averaging them if you have different data sets selected in the different folds. So kind of that understanding of what the causal parameter is one of the reasons why I like what I did, but you might also not end up with exactly the best, bias variance trade-off. Like you potentially could have achieved a numerically better answer by optimizing the bias variance trade-off if you did it in a more continuous fashion. So that's something that our method doesn't do.
Okay, and then how about this parametric correction? Is that a plausible thing to do, or is it just a silly idea?
No, it's a great idea. And there is a really interesting literature about negative control outcomes. So I explained it in a relatively straightforward way. If you don't want to make those assumptions that I made, like particularly the additive equiconfounding assumption, there are methods where you can use a negative control exposure as well as a negative control outcome to try to get the magnitude of the bias correct, even if it's on a different scale for your negative control outcome compared to your real outcome. And I'm trying to think if I know of, I'm pretty sure that I have read a paper where they do basically what you're saying, but I can't remember exactly who it is. I think some great people to look at on this topic. She et al., there's 2 papers from 2020, and Mao et al., I think that's also from 2020. They have some great examples. And I think all of those papers, or at least some of them, are cited in the references if anyone wants to take a closer look.
Great.
Thanks.
Thank you both. All right, I'll move on to wrapping this up. Just a second. All right, thank you again, Robin and Lauren, for a really nice presentation and discussions. I think it's a very exciting area of research. Yeah, I was very happy to see the talk. Looking forward to reading the references, actually. Missed many of those. Okay, next week we have a talk by Stijn van Steeland from Ghent University. So hopefully you will all join us for that. Have a great week, everyone.